Welcome to aminacademy.com. In physics, regarding mechanical properties of solids, let us do some solving problems. Look at this example. A steel wire of length 1 meter has cross-sectional area 1 centimeter square. If Young's modulus of steel is 10 power 11 Newton per meter squared, then find the force required to increase the length of wire by 1 mm. Here, the given things, length L equal 1 meter, cross-sectional area A equal 1 centimeter square, which is equal 10 power minus 4 meter square. The modulus of steel, that is Young's modulus, Y equal 10 power 11 Newton per meter square. Then find the force required to increase the length of the wire by 1 mm, that is delta L equal 1 mm, which is equal 10 power minus 3 meter. Now, here we know that delta L equal FL by A, the force into length divided by cross-sectional area into Young's modulus. Here, the delta L is given 0.001 meter equal F force is, we need the force, length is 1 meter over cross-sectional area 10 power minus 4 into delta Young's modulus is 10 power 11 Newton per meter square, which, look at here, after that from here we will get F equal 0.01 into 10 power minus 4 into 10 power 11 by 1, which is equal, therefore F equal 10 power 4 Newton. Next question. A steel wire of length 4.7 meter and cross-sectional area of is 10 into 3 into 10 power minus 6 stretches by the same amount of copper wire of length 3.5 meter and cross-sectional area is 4 into 10 power minus 6 under a given load. The ratio of Young's modulus of steel, that of the copper, we have to find the ratio of the Young's modulus of copper and steel. Here we will write steel, copper. Steel length is L1 is 4.7 meter. Copper length is 3.5 meter, that is L2. Then same amount of wire, length of the wire we got, and area, cross area of steel is 4 into 10 power minus 6 meter square. For that, same amount of copper wire 3.5 and cross sectional area 4.6 under a given load. Here and for a steel is, for steel cross sectional area, A for steel is given 3 into 10 power minus 6. So A for steel is that is A2, we can write is 4 3 here 3 into 10 power minus 6. Now we have to compare Young's modulus of these things. We know that delta L equals FL by A. From this, you can put, instead of E, you can put Y here. Therefore, from this, the ratio Y1 by Y2 equal L1 by A1, L2 by A2. From this combination, you can write which is equal L1 by L2, A2 by A1. So, length is 4.7, L2 is 3.5 into cross-sectional area of A1 is 4 into 10 power minus 6 over A2 is 3 into 10 power minus 6. So by simplification, we get which is equal 1.8. Therefore, ratio of the Young's modulus is 1.8 to steel and brass. Next question. A rod of length 2 meter is suspended from the ceiling horizontally by means of two vertical wires of length tied to its end. One of the wire is made of steel and is under its cross section 10 power minus 3 meter square, and the other of a brass cross section is 2 into 10 power minus 3 meter square. Find out the position along the rod at which a weight may be hung to produce, that is Young's modulus of the steel is 10 power 2 into 10 power 11 Newton per meter square, and for brass is 10 power 11 Newton per meter square. For equal stress in both wires, for equal strain on both wires, we have to calculate the ratios. Here, stresses are, we know that F1 by A1 is equal F2 by A2. That means force by steel by cross section area, then is force by brass divided by cross sectional area. These ratios. From this, we can do F1 F2 equal A1 by A2. The ratio is given. Cross sectional area is cross section of brass is 2. That is here 10 power minus 3 over 2 into 10 power minus 3, which is equal 0.5. That is ratio of the forces of steel and brass is 0.5. Now, from this, therefore, you can write 2F1 equal is F2. Is the force on steel is equal to force on the brass. Now, the total weight W is equal F1 and F2. That is F2 by 2. F1 is F2 by 2 plus F2 equal 3 by 2 F2. Therefore, we can say F2 equal 2 by 3 W. Now we have to equate the torque. Equating torques the both, that is, let it be W into X equal F2 into 2. Therefore X equal position of the weight, that is 2 by 3 into 2, which is equal 1.33 meter. That is the position of the weight hung is 1.33 meter. Next question. A vertical steel post diameter of 25 centimeter and length 2.5 meter supports a weight of 8000 kg. Find the change in length produced. Yeah, the simple case, it is delta L equal FL by AY equal 4 the change. A vertical steel post support a weight of 8000 kg, a 8 not 4, 8 into 10 power 3, length is 2.5, A 25 centimeter, diameter is 25 centimeters, pi d square by 4 here, that is 5 into 0.25 square by 4, and length Young's modulus is 2 into 10 power 11. So which gives, after simplification, we get 0.0021 meter, which is equal, one more zero here. Therefore, we can say it is 0.021 mm. One more question. There are two wires of same material and same length, while the diameter of a second wire is 2 times the diameter of the first wire. Then the ratio of the extension produced in the wires by applying same load will be. Here we know that delta L equal FL by A. From this we can write Young's modulus O equal FL by A delta L. Now both the same material, therefore Young's modulus is equal Y1 equal Y2, that is FL, same length L, A1 delta L1 equal FL by A2 delta L2. Since load and length are same for both, load and length equal, load length are equal, therefore load and length means FL cut, therefore we can see the ratio can be written as radius r1 square delta L1 equal r2 square delta L2 square. From this we can get it delta L1 by delta L2 equal r2 square by r1 square, which is equal r2 by r1 the square equal here there are two material same length while the diameter is second is 2 times the first, that is equal, that is 2 square, 2 by 1 whole square, 2 square equal to 4. Therefore delta L1 ratio delta L2 equal 4:1. So far I have done 5 problems along mechanical properties of material. If you have done, please subscribe our YouTube channel.